This video is going to be a demonstration of how you can measure and compute the original volume and surface area for a rectangular box. I have a box of pasta. At the very bottom, it gives you the volume as 16 ounces. We're going to convert that into cubic centimeters in a couple minutes. We're going to need to figure out the dimensions of the box. So we're going to need to figure out the length, the width, and the height of the box. If you have a ruler, it's easy to do. You just line them up and measure. However, if you don't have a ruler, there's grid paper that I've provided in Canvas that you can print out. Just make sure when you print it out, you do 100% so that it winds up being exactly 1 centimeter per box. Then the same thing. We can just literally put the box on top of the grid paper, figure out the length, the width, lay it down, and figure out the height. Now that we've got the measurements of the original box, it's time for us to try and figure out what the optimized surface area would be. So I have the volume of the box as 16 ounces times the 34.413. This is the dry measurement. We'll do a separate video about if something is a liquid measurement, what do you use for the conversion. But in this case, I got 16 times 34.413 and came up with a volume of 550.608 cubic centimeters. That's our constraint. We do not want to fit less than that amount of pasta into the box. When I measured the dimensions of the original box, the width of the box was 7 centimeters, the length was 14, and the height was 18. Now, in the directions, it talks about for these types of rectangular prisms, we want a relationship between the length and the width. Well, we're going to say that the length is 2 times the width. So we'll call this W. We'll call this 2 times W. And then the height, we're just going to call H. Now the surface area, there are 6 sides to the box. There are the top and the bottom. There's the front and the back. And then there's the sides. There's 2 of each, so that's why there's a 2 in front of each of these areas. So the total surface area of the original box is 952 centimeters squared. But we want to see if we can make that smaller, so we're going to use our constraint to find out if we can in fact make a smaller box. So the constraint is the volume. Well, the volume of the box is going to be its length times its width times its height. So that's our constraint equation. I want to solve it for H. So I now have that H is equal to 550.608 divided by 2W squared. I'm not going to simplify that. I'm going to leave it alone. But now I need to use that in the equation for my surface area. So I'm going to stop for a second and see if you can determine what the surface area formula would look like for the rectangular box. So my surface area formula is now written underneath the picture. It's 2 times the length times the width plus 2 times the length times the height plus 2 times the width times the height. What's important to know is now I need to use the constraint and replace H in both parts of that area formula. So you can see that I've replaced H in both the second and the third part of my area formula with the expression that h is equal to. Now I can simplify now or wait. I'm going to wait for another step before I simplify, because if I notice, these two terms are really the same, and so I'm actually going to be able to combine them. I have 4w plus 2w, which is 6w times the like term. Now I'll simplify. And I'm going to bring this w that's in the bottom up to the top and write it with a -1 exponent. I'm now ready to take the derivative of my area formula. Taking the derivative, because that's how I find out minimums and maximums, by taking the derivative and setting it equal to 0. So the derivative would look something like this. And that becomes a form of my derivative, and I'm going to rewrite it like that. I want to know where this derivative is equal to 0. And so I'm going to bring this fraction over to the other side. And I like to cross multiply when I have proportions. So I get 8w cubed equals that big decimal. Divide by 8. And then I'll take the cube root. And I get that the width is equal to 5.91 centimeters. Now, that's just one dimension. I need to figure out the other dimensions. So the length is going to be 2 times that. And the height is going to be based off of that constraint equation, the 550.608 over 2 times my w value squared. So now those are my new optimized dimensions. You'll notice that they're all smaller than the original dimensions of the box. But the true test is, what's my new surface area? Well, my new surface area is going to be 2 times the length times the width plus 2 times the length times the height plus 2 times the width times the height. And this is where you really see how much different the new minimized area is, because this new area for the box is now 419.14 square centimeters. The original was 952 square centimeters. So that's a big difference. Part of what you would have to do in your report is say, why do you think there was such a big difference? and if you would keep the original shape or the original dimensions of the container, or why you would want to move towards this new minimized surface area.